or to cloud. Okay, then let's continue our discussion about the simple graph algorithm, that example. Okay, we have a couple of more haven't discussed yet. And so last class we discussed like depth first search, breadth first search, is it, and the cycle check, so those ideas. And so the depth first search, that idea, you can also use it to check if there is some certain path on your graph. Okay, so here I provided this method has path, and this path is to check if there is a path exist between two vertices that you specify, source and destination. Okay, and then the third parameter is an array list called path. Okay, so this path, it says it records all vertices visited. Okay, not the path from source to destination. Okay, and the path is recorded in predecessors. Okay, so that's what over here the general data structure that we used here. Okay, so let's probably, not sure if we still remember what so for this simple graph, we have two instance variable. Okay, one is vertices, and the vertices is each vertex has the adjacency edge list, is it? So it's a list of the edges that's adjacency to this specified vertex. So this is one instance variable. The second is predecessor. Okay, so predecessor will record the parent and not, so the kind of like a parent-child relationship between the two vertex. Okay, so this is regarding directed graph. Okay, and we use both. We use map. Okay, use map. So here is key and here is a value, etc. And for the predecessor, the value is another vertex. Okay, so that's what a predecessor is. And then for that path, so okay, so then for this path here, that's the predecessor used to backtrack from destination to source. Okay, so if you want to get to the route, then from the source to destination, you can use predecessor to get it. Okay, so that's what this method will give you to find the path. Okay, then how do we do it? So first, so it's kind of similar as depth first search, okay? Because it's trying to find a path, is it? And of course, depth first search applies, is it? So first, so source is the starting index, okay? And then you set it's visited to true, okay? And then you add it to this array list. Array list, the path, it just records all vertices that's already visited. Okay, so that's just record all visited vertices. And it says if source equals to destination, because over here we are going to use recursive. So here we do the recursive implementation. Okay, do recursive, so the source is going to be changed. Okay, so that's why if it says the source equals to the destination, then you said you return true. That means you find the path from the specified source to the destination. Okay, and then what we can do is, because this is regarding directed graph, is it? So maybe you have some other. So anyway, it's something like this, is it? Or maybe more, is it something like that? And so for each vertex, you can call the get successor vertex. So in this case, the successor are these two nodes, as a two vertex. Then for each of it, it says if it is not visited, as if it is not visited, so then you're going to add it to the predecessor's map. Is it predecessor map? So here is the source. Here is source. And here is the current vertex. Is this because this is a predecessor? As a predecessor. Okay, and so this is regarding the map method. You add a new key pair, key value pair, as it to the map predecessor. And then what? You can call hasPass, you recursive call hasPass again. So this hasPass, then it's moved to this vertex, is it? To this one, and this destination path not change, is it? And if it is true, that means you find it, is it? Otherwise, it will keep doing, is it? Otherwise, it will keep following the path, is it? So it will do the depth first search. So this is a concept, is it? But along certain paths, if it find, is it? The predecessor will give you the path, will let you backtrack from the destination to the source. Okay, so this is a hasPass. So hasPass is, you can see it's not that complicated. Okay, and and then in this program, I also have this get a predecessor, is it? And then it returns the map. So it gives you all of the predecessor, okay. Okay, and what next we needed to go over is another concept. It's in graph. This is for directed acyclic graph, so DAG, okay. For DAG, you can use it for task scheduling. Okay, and with a concept, we call it topological numbering. Okay, and then in this case, you can use graph to represent tasks. Okay, and because it's tasks, and it's also directed DAG. As I said, each directed edge UV then represents what task U needs to be completed before starting task V. So U and V task. Okay, task U to task V. So this is, in this case, considered as task. And this is called task V. Is it? And UV. So that means if you want to complete task V, task U need to be complete first. Is it? So that represents the relationship between two tasks. Is it? And then here it says to find out the dependencies among the vertices, we can use a technique called topological numbering. Okay. Can be applied to each vertex, a unique integer number, and that number is called topological number. Okay, and then in this case, the vertex topological number must be smaller than all of the successors topological number. Is it? So number in this case going to represent which task going to be complete first. Is it? So then in this case, if this number, suppose V is 2, then U can only be 1. Is it? So the predecessor's topological number needed to be smaller than the successor. Successor's number needed to be greater than the predecessor. Okay, but think about, and sometimes you may have multiple leading edge. is it? So how do we handle that case? So we first take a look. How about let's first take a look the diagram to help us understand better. Then we can go back. Okay. So basically, in this diagram, is that so this diag is directed acyclic graph. Okay, and over here you can see by each vertex we have a number. Okay, so this number basically is called topological number. Okay, topological number. And in this diagram, we start at A, task A. So its task is 1. And then next you finish task B. Is it? So its number is 2. And then task D, it depends on both task A and B completes. Is it? That shows. So this task depends on 2 tasks, 2 previous tasks. So its number then needed to be 3. Is it greater than the previous to the larger one of the previous 2? Is it? And then for C, then definitely it depends on both previous tasks. Is it? So that's why its number is 4. Is it? And the E, then its number is 5. Why? Because it depends on both previous tasks. Is it? And then similar for task 6. Is it? Depends on the previous task. And from this task, is it? And we can redraw the graph, kind of, show the task relationship. As a task relationship. And then here it gives the dependency. So we can clearly see dependency relationship. Is it? It's quite clear. And you can also find like the number. Is it? Okay, so that's regarding topological numbering. And then let's come back to see how do we find the topological numbering. Okay, find dependency vertices. And here's a similar as checking if a graph has a cycle, is it, with a specified vertex, is it, is that we can do topological numbering, okay, with a starting vertex, and you also pick a number, okay, and we can use a similar technique as depth first search. Okay, depth first search. And here that's because this is DAG. DAG doesn't have any cycle. Is it? Doesn't cycle. So it says there must be at least one vertex that doesn't have any successor vertex. So in our graph, it's F. Is it in our graph that vertex F, it doesn't have any successor vertex. Is it? And then this vertex should have what? The largest topological number. Is it? And it is also the vertex that terminates the search when we do the depth first search. Is it? And we can mark the status flag as done. If you recall previously regarding topological, is it? If you just say visited or not, that won't work. Okay, so we have 3 modes for the node status. Is it non-visit, visited, and done? Okay, done means that what? That all of its successors already taken care of. Is it? And for this case, because it's DAG, is it? Node F is the last node. Is it? That doesn't have any successor. Is it? So it should also have the largest topological number. Is it? So we can mark it as done. Okay. Okay, so this is regarding topological, and then let's go back to the coding to see how do we how do we implement this topological number, okay, method. And over here, okay, for the topological number, is it, we have the vertex, we also have number, okay, and this vertex is a starting vertex. Starting vertex. And this number, be careful, okay, this number is the largest number. Largest number in the topological numbering. Okay, that's what we are going to not. I shouldn't see the largest. So so not shouldn't say the largest. Okay, so you gave some number. Okay, so you can pick a number, and then because all of the predecessors number are going to be less than this number. Okay, but this number, not the largest. Be careful here is this number is not the topological number for starting vertex. Okay, be careful. This number is going to be the vertex that doesn't have the successor vertex. Okay, so anyway, so it's not the starting one. Okay, so then let's see how do we do it. So we are also going to do the recursive way, okay, for the topological number, okay, and it's also similar as depth first search, okay, for topological numbering. Okay, then let's see how do we do it. So specify a vertex, is it? And then we are going to mark its flag as what? As in progress. Okay, as in progress. And then for each of its successor nodes, okay, if it's successor, and if its flag says in progress, that means it's a cyclic graph. For cyclic graph, the topological numbering won't work. So that's why here we said throw some exception, okay, because there is a cyclic graph, okay. And otherwise, you're going to check if the flag, it is down the mode, is it? If it is not down, is it? Then you are going to call the topological number again. Okay, and this time you plug in what? It's successor. That is a successor, and with the number. And the topological number returns what? Returns a number. Okay, returns a number. So you're going to call so recursive call its successor node. Is it? So this is among all of the successor vertex. Is it? And when you complete, so this for loop, so when you complete the vertex, a specified vertex is all successor nodes. Is it? All of its successor. If you complete all of it, then you mark its vertex as done. Is it? And you get the number. Assign that vertex. So this is that vertex, is it? To that specific number. Okay. And you return -1. Okay, you return -1. So you can see this is keep decrement. Decrement. Is it? If you draw a stack, is it, and tracing it, and you will find at, so it's whenever it reaches like that F node, is it? Then it's going to back the number, is it? So that's why the number is going to be back, is it? Okay, so that's how we do the topological number. Okay, so it's a recursive call. Okay, when you do the recursive, you keep calling successor nodes, etc. But on the stack, how you get assign the topological number to each of the vertex, etc. That's its backtrack, etc. Okay. Okay, so this is regarding the topological number. Okay, so we are done with, we go back to our slides. Okay, we are done with that example. Okay, and the next one, what is the next one we are going to take a look is, what we are going to take a look is the weighted graph. Okay, we haven't discussed this. Weighted graph. Okay, weighted graph. So what is the weighted graph? So here it shows. So weighted graph is each edge. So each of the edge, and here it has direction, etc. So edge also has cost, or we call it weight, associated with it. Is it? So here we have 2, here we have 3. Is it? And from A to C we have 8, we have 5. Is it? From B to C we have 3, we have 6. Is it? From C to L we have 5, we have 8. Is it? And between C and E we have 1, 1. Is it? So all of these numbers give us what? Give us the weights. Is it? And the costs. Those. So if you have a graph and you also have weights or costs associated with the edge, then the graph is called weighted graph. Okay, weighted graph. And for weighted graph, this is not just for weighted graph. Okay, so from graph you can also find we call it a spanning tree. Okay, so from any vertex, okay, from any vertex, and you can reach the other vertex. Okay, you can reach the other vertex, like in this case. Is it? You can always reach the other vertex. Okay, and like in this case. Is it? Through some path. Is it? And the path doesn't include any cycle here. Is it? So anyway, because it's a tree, is it? So from any vertex, you can reach other vertex along a path, and there is no cycle involved. Then you can come up with a tree, is it? And that tree, we call it a spanning tree. Okay, spanning tree. And there are a lot of trees, because you can go through multiple paths. It's a different path will give you different spanning tree, is it? But among the tree with weighted graph, is it? And we can have a concept, we call it minimum spanning tree. Okay, minimum spanning tree is what? Is among all of the spanning tree, if you add the costs from all the edges from the tree, is it? So from all edges of the spanning tree. And if it is minimum, one, is it? Then that tree is called a minimum spanning tree, is it? So like this diagram, it shows this one is a minimum spanning tree, is it? Because if you just think about it, if if I redraw something, is it? So I get like from A to B, is it? And then A to D. But I may not go through like I will go with like from D to C, is it? D to C, and then C to F, is it? And then F to E, is it? You can also come up with some tree like this. And if you add the cost of this tree, not this one, is it? Compare with the one we draw here, and the cost is going to be larger than this one, is it? So then this one is among all possible spanning tree, and the cost is going to be the minimum one. So this one, then we call it minimum spanning tree. Okay, minimum spanning tree. Okay, and that's minimum spanning tree. Okay, and then let's take a look. Okay, I first need to find my, so this is from another example. Okay, from my weighted graph. Okay. So now I have, so for the spanning tree and some other algorithm, because it's more related with the weighted graph, so I put it in a weighted graph example, okay? In this example, we also have vertex, edge, and the weighted graph data structure and the driver part, okay? And then let's take a look at the vertex, okay? For the vertex, we have ID, we have label, is it? And then we have some flag, okay, some other information, okay? So this vertex is pretty similar as what we previously learned, okay? And the vertex flag, we have three status: unvisited, in progress, and done, okay? And then let's take a look at the edge, okay? For edge, we have two vertex, no doubt, okay? And we this time has the weight, okay, has the weight. And the weight is also called cost, okay, in some cases. And over here, we also have a Boolean variable called directed, okay, to indicate if the edge is has a direction, okay, and the direction is from U to V, okay. And for this edge, because we are going to assign weight, is it? So each edge is also going to be assigned with the weight, okay, for the constructor. And for the directive, we just set it to false initially, okay. So that's regarding edge. And then toString, it's pretty similar, and the equals and pretty similar hash code also we conducted here, okay. So that's this edge. And then let's take a look at the weighted graph part, okay. For this weighted graph, similar, we have the vertices and the predecessors, okay. But because we also have costs associated, is it? So because anyway, so over here that you also, so we also define the cost and associate with the starting vertex of the edge, okay. So this is the data structure part, how we define it, okay. And for the weighted graph, then we initiate the vertices, the predecessor, and the cost, so all associate them with the hash map, okay, hash map. And then let's see, whenever we add vertex, is it add vertex? So it's a new vertex. So this is similar, is it? Because it's a map, is it? So you can call maps as put if absent, is it? You specify the vertex, and then you're going to associate with a list, is it? With a list. So this part is similar. And then for edge, okay, and for the edge, is it edge because it's associated with weight, is it? So that's why whenever we add edge, we also need to associate with the weight, okay, with the weight. And for the edge, then we can get, we call the maps as get method, as we get all of the values. The value then is an array list, so we can loop through each of the edge, is it? And if it's already, then you just return, is it? Otherwise, what you can do is you create a new edge, is it? And then what you do, you add this edge, is it, to the vertex, to the map, is it, associated with that specified key, okay? So that's how this part works. So here we have some update for weights and for get neighbor vertex, because it has nothing to do with weight. So it's similar as what we discussed before, okay? And then next, let's see, how do we find the minimum spanning tree? Okay, so here is the code. So we do the prime, we use the prime algorithm to find the minimum spanning tree. There are some other algorithm, okay? But here we pick this called prime algorithm to find the minimum spanning tree, okay? So let's see, you can specify a vertex, okay, specify vertex. And here we have two sets. We set up two sets, one is called included, the other is called excluded. Okay, so let's see how this algorithm works based on this coding, okay? And initially you put the included, you put the origin vertex to the included, okay? And for excluded, it should be all of the vertices of the other vertex. So you can call the get vertex. So this will give all of the vertex of your graph, but you need to remove the starting vertex. The starting vertex. Okay, so we have included and we have excluded. It's both are the two sets. So you have two sets, is it? And you have origin and the of the other others here, the vertex. Okay, and then what we are going to do is we are going to use a loop from excluded. Okay, from excluded. So when excluded is not empty, you're going to keep this loop. And because here it involves minimum cost, okay, so I'm going to use a quite a large number, okay, set as a minimum cost, okay. And I'm also going to keep track of the minimum vertex, okay, and the respective edge, okay, with the vertex. And then how do we do it? Here is from the included set, we are going to do the loop, okay, to do the loop. And the loop is then from each of the included set, you find what? Edges, is it? You find all of the edges related with the included set. And then you will find what? If the edge also contains a vertex that's in the excluded one. Okay, excluded one. And then you are going to check if the minimum at this point, if that minimum cost is greater than this specific edge. So wait, if it is, you're going to update it. You're also going to keep track of the minimum vertex and the edge. And this going to record, is it, which vertex you are considering at this point. Okay, you're considering at this point for this minimum vertex, is it? And this V is the edge, is it? So it's the other end of the edge. The other end of the edge, it's included in the what? In the excluded, so not considered yet. Okay, so you will try to find from the excluded set of the vertex. And so you have two vertex, is it? You're going to try to find the cost. Okay, so this is in the included, and this going to be from excluded. Okay, so you have more, is it? You have more, is it? And you're going to do one by one check, is it? First, you from the included, you can find if it has some other edges, is it? And you also need to make, because it may also have the edge already, so the other vertex also in the included. Then you are not going to consider. You will only consider the vertex from excluded part. Okay, excluded part. And then you're going to find the edge. Find the edge, which edge? The smallest cost one. Is it? Because you already use that minimum cost to keep track which one is the smallest. Then you're going to find that one, is it? Then you're going to update the vertex, is it? I update the vertex, so this is going to be suppose minimum vertex. Okay, and you're also going to update this minimum edge. Okay, update that for this loop, is it? For this loop, then you will basically find it, is it? And after you find it, what we are going to do, you're going to add that vertex from the excluded one, is it, to included, and you remove from included. And then you also keep track of the predecessor, is it, of the newly found vertex, is it, keep track of, and its predecessor as who, is it, from the edge, the minimum edge. And in this case, we so for our program, we are going to output the edge and the corresponding cost, okay, for the minimum spanning tree, okay. And then if you take a look, so this loop ends when all the nodes from the excluded are considered. So that means you find the path to all of the nodes from the graph. And then we are done. Otherwise, if the excluded not completed yet, so each time you are going to go from the included one first, find the edge from the other end is from the excluded, is it? And then you find the minimum cost one. Okay, you find the minimum cost one. And for the minimum cost one, you are going to add it to the included. Okay, and then remove it from the excluded. And then in this case, we can keep track of all of the predecessors, and then you can output your the cost and the edges. So basically the tree, okay. So that's the coding part. And then let's see, I should have the example. Okay. Example. Here is my example. Okay, I cannot find it. So how about let's do not digest yet. Let's go back to the previous slides. Okay, we can kind of keep tracing of this one. Okay, so this is the original diagram. This is the original graph, is it with the width? So suppose we want to just see if we can get this graph, okay? So we will start with A, is it? So start with A, so A is included, is it? So you have included is A, is it? And with A, then you are going to find its edges, is it? We are going to consider this direction, okay? So over here, we consider the direction, okay, here. So from A, is it the related edges, or we should also consider this one. The three edges, is it? Among the three edges, you will find the minimum cost one. Who is the minimum cost one? This one, is it? It just has one, is it? And also, okay, we also needed to have the excluded set. Excluded set is what? Is B, C, D, E, and F, is it? So you are going to consider from the included and to the excluded, is it? Because it's not included yet. It's the tree, is it? So from the included to excluded and find the minimum one. So D, then in this case, is the minimum one. So you're going to remove D from excluded and add it to included, is it? And then you mark down D, is it? And in this case, you can also mark down the predecessor of D, is it? Is from A, is it? And the cost you can also record it, it's one, is it? So basically, this part we get it, is it? Okay, after this part, and then next, what you are going to do, you are going to continue from like included to excluded. Okay, then included to excluded, this time we have A to B and A to C, is it? But you also need to consider D, is it? And D can also go to B. Is it? D can also go to B. D can also go to C, is it? And D can also go to E, is it? So among all of this, and what? And here, is it? And this one. So all of the dashed line. Among all of this, which one has the smallest cost? Then we can clearly find this one has the smallest cost. Is it? It is one. Okay, so we are going to, and the node is E, is it? So you are going to add E to included and cross it out, is it? So E now is included, is it? So you can also mark it down like then D to E, is it? And the cost is one, is it? Just shown like here, is it? Basically, we already got this part down, is it? And then same thing, next, you have 3 included and 3 excluded. So you need to keep track of, okay, from A to B and A to C and D to B, D to C, etc. And then also E, etc. From E can to, oh, I think I need to use a different color. Otherwise it's messy. So let's see. So this time A to B, not to consider yet, it's 2, etc. And A to C, etc. So this one also not to consider yet. So it's 8, etc. That's from A. And then from D to B, not to consider yet, it's 2, etc. And D to C, also not to consider, it's 3, etc. And D to any, no. And then what? Then we have E, etc. E to C, etc. It's 1. And the E to F is 2, etc. So we have all of those red color edge highlighted, is it? So among them, you need to pick the smallest one. Is it who is small? Then we can see this one is smallest one. Is it? So C, then in this case, should be included. Is it? So you add C and you mark out from excluded. So now C is also included. Is it? So it's spanning. Is it? So why we call it spanning tree. And then next, then you need to, from this 4 included, is it, to the 2 excluded, is it? Then we need to find the smallest. Is it smallest? Then here we run with some time. Is it A to B? D to B, both are 2, is it? And E to F is also 2, is it? So assuming over here, I try to follow this. I'm going to use a different color. Probably let's pick this one. And the B is not included. So we pick this is 2, is it? And D can also to B. It's 2, is it? And C can also to B, is it? It's 6, is it? And what else? So to B, then to F, is it? To F, you have E to F is 2, is it? And C also to F, it's 5, is it? So among them, definitely 2 is the smallest. So I can pick just this one, is it? So then B is also included, is it? B is included. So you needed to get B here and remove B from, and the last one just left, the last one. And of course, you needed to find the minimum cost one from the included to the excluded, is it? So you can find, okay, from E to F, this one is the smallest, is it? So then you add F also to exclude. Oh, I forgot. At the same time, each time when you add to the, you also record the edge, is it? And the cost, is it? So then you see, you can find the tree, is it? You can find this tree. And this tree, then all the cost, if you add together, it's the minimum one among all of the other possibility. Okay, so that's why over here we call it minimum spanning tree. Okay, and the algorithm that we discussed is called the Prim algorithm. Okay, Prim's algorithm. Okay, so this is a discussion about minimum spanning tree. Okay, the Prim's spanning tree discussion. And the last one, then in this section is about shortest path. Okay, the shortest path. So over here, we are going to discuss, it's called, oh, I didn't share, I'm sorry. So the last one in this weighted graph discussion is that's also used a lot. Is it in graph? That's also very very common question. Is it you want to find the shortest path? Is it in the graph? Suppose from one starting node, so from one node to all other nodes, the shortest path. Okay, how do we find it? And there are also a couple of algorithms, okay, popular. And what we will discuss the Digester's algorithm, okay. So, and it's also regarding the weighted graph because it's trying to find shortest path, okay. So this is quite useful. Is it like if you want to like the routing, is it and from one city to the other, is it you want to find using the shortest path and with provided graph, is it? So that's one of the available approaches is to do the Digester's algorithm. Okay, then over here, the question is how do I show the algorithm? This graph is already kind of full. So let me see if I can clear it out and see kind of. Let me see, probably I'm going to just draw. Let me see if I can minimize a little bit, give more space, okay, so that I can draw. Let me see for this, can I view it? I will just try with this, okay. So the algorithm I'm going to explain, I will use a table to explain the concept, okay. The algorithm that it can help you understand, and hopefully this color still works, okay. So here we are going to do the iteration. So it involves a number of iterations, okay. And then we have included a set. So it's a set, okay. And then we have, so it's starting from A, okay. So here, source is A, okay. And then we are going to consider from A to all of the other nodes, okay. So to B, okay, and the path, and then to C, to D, to E, and to F, okay. So for all of this, okay. And starting from iteration 1, and then the included set. So here it's similar as the Prim's algorithm. At this point, we only have node A included. Okay, node A included. And then from node A, you can reach which other nodes? Is it? So you can reach node B. Is it like here, my purple line shows. So you can reach B. You can also reach D. Is it? So here it record all of the paths. Okay, all of the paths to of the other nodes. So to B, then it's A to B. You can mark it. And what is cost? The cost is 2. The cost is 2. And A to D is what? The cost is 1. A to D, the cost is 1. And to C, A to C, we can also reach it. Is it A to C? It's A to C. It's 8. Okay. And A to E and A to F, there is no path. Is it? So we can consider the cost going to be infinity, the infinity. Okay, so this is the first iteration, okay. So you consider the included set and then find all of the edges and then find all of the edges and the cost, is it? And from the edges you find what? Find the minimum one among the cost to the nodes. So which one is a minimum? Then definitely this D, A to D is the minimum one. Is it? And if it is a minimum one, then for the second iteration, you are going to add D to the included set. Okay, add D to the included set. And after you add D to the included set, then let's see the path to each of the paths. Okay, so A to B, A to B, is it? Let's see what path we have. We have the original A to B, the cost is 2, is it? And now because D is also included, is it? If D is included, that means you can also use A through D to B. Okay, so we can also do A to D to B. Is it? A to D to B. And the cost is what? It's 1 plus 2. 1 plus 2, it's 3. Is it? So that's also possible, is it? And then the other available is A to B. Then you need to compare these two, okay, to see if this new path through this new added nodes, if it's better than the previous available one. And looks like it's not better, is it? So if it's not better, then we don't need to update. So you just keep this old one. Okay, keep this old one. Okay, then let's see to C. To see the old one is 8, is it? And then now you have D is also available. So you can see through D if you have any path. And of course we see through D you have DC available, is it? So D to C is the edge. So D is successor, is it? And you can find this edge. And you already know A to D, is it? So A to D and D to C, is it? So the total cost is what? Is 4, is it? Is 4 in this case. And is this better than the previous one? And we can see it's better, is it? So this time you update as A to D, then to C. And the cost is 4. Okay, and then to D, we can clearly see there is no updates. It's a solid itself. Okay, and then let's see to E. So previous just go with A, there is no path, it's infinite. Now through D, let's see, D to E is also available, is it? And A can go to D, is it? So we have A to D, no, A to D, and then D to E, is it? D to E. So this path, the total cost is going to be what? It's going to be 1 plus 1, so it is 2, is it? So this you can update as A to D and then to E, and the cost is 2, is it? And to F, can we reach? We can still not. So it's still infinity, is it? So this is the second iteration you finish, and among that, then you're going to find the least cost one, the minimum cost one, is it? Among this, D already included, so the N included nodes, is it? So we have A to B is 2 and A to D to E, is it? So among them, suppose we pick B. So then you run into the third iteration. So it's A and D and B, is it? So now you include B. So with B newly added, then we need to find the path, is it? So A to B, then definitely you cannot see any update. Is it better than that? Okay, and with B added to C, let's see if we can have better choice. Is it? With B added, you go A to B and B to C. Is this better? So this is 5. The previous A, D, C is 4. Is it? So it's not better. Is it? So you still keep this old one. And A to D and through B. Is there any good choice? There is no good choice. So you just keep this old one. And to E through B, do we have any updates needed? We can see there is no updates we can do, is it? And then to F, is it? To F through B, then clearly we cannot see any good updates, is it? So we can just keep this. Okay, keep it as infinity. So now let's see. Among this, we have the not included one is C, E, and F, is it? And then let's see the cost. A to C it's 4. A to E is 2. A to F is infinity. So definitely E is the minimum 1, is it? So then you need to go to iteration 4. Okay. And then you add like A to D to B, then to E, is it? With E added, then you need to figure out if there is any updates needed, is it, to each of the paths. Okay, then we can see for E, then you can go to see if to D, to everyone else updated. And we can see from E, if you want to go through E to B, there is no better choice. So you keep this one, is it? And to E, then from A, you to E, it's go back to it. So that's not a shortest path, is it? You cannot let the node visit it twice. So this part also not needed to update it. Then to C, let's see. To see if you go with, because from A to E, we already know it's 2. Then from E to C, it's 1. So this is the new cost from A to E, then E to C. It's going to be 3. So this is a good choice. So you can update it. It's A, then to D, then to E, then to C. Is it? Because from this A to D to E, this path, then from E to C, this does update. It's as 3, that is the cost. And to D, you can find there is no updates needed. And the same thing to E, there is no updates needed. And then to see F, if there is any updates needed. To F, then now through E, you can access to F, is it? And the cost is 4, is it? So A to D to E, then to F, and the cost is 4, is it? Is 4. So we already add 4 nodes, is it? So now the only 2 nodes not added is C and F, is it? So between these 2, then you go to the 5th iteration, is it? And then you can add A, D, B, E, and C, is it? After you add C, then you will see if there is any updates needed here, is it? And you can find there is no updates to B, is it? So A to B is still the least cost one. And if you want to go through C, is it? So that's not a good choice, is it? And then to D, it's the same thing. To E, it's the same. And to F, it's also the same. So there is no updates needed, is it? So then the last node not included is F. Is it F not included? Then you include it, and you also find the path. Is it? So this is called the shortest path running with digester's algorithm. Okay, so there are. So here it's different from the spanning tree. Is be careful here. Okay, you also need to consider if the path updated. Okay, the cost. The minimum cost is not just the edge. You also need to consider the total cost. Okay, so the total cost so far that to certain vertex. Okay, so if it needs to be updated. Okay, so that's regarding digester's algorithm. Okay, so we kind of understand the concept, is it? So then next, let's take a look at the coding part. Okay, the coding part, this is digester's algorithm. So specify some origin. So starting a vertex, is it? And similar, we use a set to have the included, okay, included. And this functional expression, so let's take a look, it's more easy to understand, okay? And initially, for all of the vertices, so this is regarding the whole graph, okay? Whole graph. All vertices, because the get vertices is you can get all of the vertices. For each of the vertices, for the cost, is it you need to initiate with some value. So I use some integer maximum value, a very large number, okay? And also you also need to remember the predecessors, okay? Okay, so that's regarding this part. For the cost, if you remember that's regarding kind of even before you starting the first iteration, is it? And then for the origin, is it the cost? Then of course it's 0. Is it? Then we can start to do our updating. Okay, do our updating. So what over here is you're going to loop through the included. So if all of the nodes are already included, that's because it's based on the vertices size, okay? And initially you set the minimum cost as that maximum value. And similar as the prim, you also need to remember the minimum vertex, that's it. And then for every vertex, okay, then you need to check if it is included. If it is already in the included set, is it? If it is not in the included set, and the cost for this specific vertex is less than the, at this point, is it the minimum 1, is it? Then you are going to update the minimum cost and the corresponding vertex. Okay, so this part is trying to find the connected one, which one has the minimum 1, is it? Okay, but then what next part you need to do is, after you find it, is it the minimum cost 1, is it? Then you are going to add that vertex to the included, is it? If you recall, we have that table, is it finds the minimum cost, then you add it to the included, is it? And after you include it, then you need to update all the paths again, all passes cost again. Is it? That's what this part did, is it? So for all of the edge, but with this newly added one, okay, newly added vertex, is it? You're going to update the cost, okay? And how do we do it? is first you need to check the edge so that the other end is not in the included yet. Is it because you're going to find the new path? Okay, and then you can find the cost. Is it the cost? So if the cost is as greater than the cost with the newly added one, as well as the weight. And then if you recall, because you are going to consider the newly added weight, newly added edge, is it the candidate edge, to see if the cost, so this is the cost we consider from this minimum vertex, just added one, is it? And if you want to find, so from this one leading to the other not included one, is it? If this one is greater than the cost from this other path plus this new edge, then you are going to update the cost. Is it? So if you recall the cost initially, we all put all of the vertexes related cost to a very large number, is it? Because you're going to keep updating. But when you keep updating this time, you also need to consider the weight of the newly added edge, is it? Which one is the minimum one? You're going to consider that. So then you're going to update that one, is it? And at the same time, you're going to add it to the predecessors. Okay, predecessor. Okay, so that's regarding for the each iteration. If you recall, when we discussed the algorithm, is it? So this part. So this part is regarding the updating the costs. Okay, updating the costs. If you recall, for our table, we do the step-by-step tracing, is it? Because when you updated that, then you can add it, is it, to the included set. Okay, and after this, and then what we can do is, if you want, you can just use, so after this loop, then you find of the shortest path, okay, from the source to the destination, is it? To not the destination, to all of the other nodes, okay. And then over here, how do we find the path? Because we use the predecessor, is it, to keep track of all of the minimum cost edge leading vertex, is it? So then with this for each of the vertex, then you can use this loop, is it, to print out, okay, all of the predecessors, okay, of the predecessors, and then we can get the shortest path, okay, for from a source node to all of the other nodes in the graph, okay. Okay, so this is Digester's algorithm. So it's a little bit of more complicated, okay. So maybe after you go home, you can try to do some also tracing, okay, what we just showed. Okay, so